Okay, so in today's class, we are going to keep talking about the growth theory model. And specifically, like I mentioned last time, we're going to talk about a model called the endogenous saving decision model. Okay, or this model is sometimes called the optimal growth model. Okay, and this model, we will focus on the saving part. Unlike the Solow growth model where there is also saving, but we assume a constant saving rate. Namely, the saving behavior is more robotic. Okay, it's like a robot who's doing the saving for you. You don't really do any saving decision. And we want the subject or the player here, agent here, to make decision for their own so that the saving is endogenous. And saving is growth, right? Saving in Solow model, you should have learned this. Saving costs growth. So if saving is endogenous, this growth is also endogenous. Actually, there's more than one way to make the growth endogenous. We are also going to talk about another endogenous growth model in the next chapter, chapter 8. Okay, so beware of the fact that this is not the only way to do so. Let's take a look of this model. Okay, in this model, we don't even need the population to grow. Okay, so we assume that the population is a constant 1 across all trial, all time, all year. And there's a representative agent who live infinitely. And this consumer, this agent, has a preference, just like what we did before for similar to the one-sided search model that we did. Basically, is a discounted utility of consumption. Okay, so basically, the formula is like here. I discount every period's consumption, and in each period, those consumption was transformed into utility based on a utility function u. Okay, and I live for infinitely many periods, right? So this summation is also over infinitely many rounds. Okay, and this u function, we assume it is continuously differentiable, strictly increasing, strictly concave, and bounded. Okay, these are just useful in terms of proving the existence. Actually, doesn't matter that much, but basically this is just assuming that the function has some good behavior. Strictly increasing makes sense. Strictly concave is for convergence or model to have equilibrium, and bounded is just making sure that the function doesn't blow. Okay, doesn't have an infinity. We also assume that when c goes to 0, the u plus c goes to infinity. What that means is that it's impossible for you to have any period to consume 0. Because if there's any one period that the consumption for that period is 0, I will give that period just a little bit of consumption, just epsilon amount of consumption. Then because u plum of c at the point 0 goes to infinity, that means that additional consumption on that period, even though the consumption is just a little, it gives the marginal benefit or marginal utility of infinity. And obviously the cost is fixed. Moving the consumption across period, there's a cost, right? Moving from period 1 to period 2, there's a cost at period 1. But the cost is finite, and this increase, this marginal gain of utility is infinite. So obviously this trade-off is worthwhile. So it must be the case that in all period, I'm consuming something that is positive. Okay, and in each period, the consumer is endowed with 1 unit of time. Okay, and we just simply assume this has to be supply as labor. There's no leisure. Okay, notice that like no leisure and no population growth, a very strong consumption. Very strong assumption. Okay, these very strong assumptions are made because, again, we want to focus on other aspect of the model. Okay. Okay. So we again assume the production function is given by this simple function y equal f of kn, and you must feel boring at this point, and I'm keep saying the same thing, but the f function is continuously differentiable, strictly increasing in both argument, and homogeneous of degree 1. By saying homogeneous of degree 1, this is equivalent to saying that this is constant return to scale. That's the same thing. Okay. And strictly quasi-concave is also just a concave version of the two variable function. Okay, so basically that's saying that the partial derivative are concave. Not exactly that, but similar to that. Okay, and we assume that if k is 0, the production is 0. If k goes to 0, and this f1 means the f derivative with respect to the first argument, that's k. Okay, so this is basically f1 is partial k partial f. Okay, so partial k partial f goes to infinity if k goes to 0. That's similar to the assumption that u plus c goes to infinity as c goes to 0. The same thing. And if k goes to infinity, this partial derivative goes to 0. That means the marginal gain of additional capital when k is really large is basically very, very low, even goes to 0. Okay? And the capital stocks obey the law of motion, the same law of motion that we have in the Solow model. So this period's this period's KT will be depreciated, and then plus the investment in this period become the capital in the next period. The same law of motion. Okay, so we must have an endowment of capital at period 0 or period 1. Okay, at period 1, we must start with some k. That's k0. And in equilibrium, we must have the labor being supplied for all t. That's because we assume the consumer has 1 unit of labor at each time t. And we assume there's the only way to use this time is used as a labor. So in equilibrium, it must be the case that this is all supplied to as labor, right? Otherwise, there must be a way to improve the production. Okay. So since nt is always 1, it is convenient for us to simply define a function called h of kt, and h of kt is just f of kt and 1. Because there's one variable that we never use. So, and if we do this, then the resource constraint of this economy, the expenditure identity will be C plus I equals H of KT, because H of KT is just YT. Okay, that's the total production. Okay, and if we use the law of motion to insert here, then we will get a relationship between KT and KT plus 1. Okay, we are always trying to get some kind of dynamic like this. We do this in the Solow growth model as well. Why is that the case? Remember, K is the most important variable that's changing over time. Or later we'll talk about this as the state variable. Okay, in the dynamic programming language, we call this state variable. This variable is the most important one, so we want to know what is the relationship between the capital in this period and the capital in the next period. Okay, so that's why we're always trying to get this kind of equation. And the social planner's problem is simply that we are solving a infinite period maximization problem. Each period we decide CT and the KT plus 1. Okay, because we sort of it is the case that if we decide CT, the KT plus 1 will be determined just automatically. Okay, because if you decide CT, this is sort of fixed, right? Because this is what I have, what I get from the last period, the capital stock I have. And if you decide CT, then that will decide IT. And IT together with KT will decide the KT plus 1 in the next period. So although I write CT and KT plus 1 here, but basically CT will always decide the KT plus 1 next period. Okay, and given K0 and constraint on for each t, this equation must hold. This equation is just this equation. Okay? And this problem is very difficult because we have infinite number of period to solve. Okay, we have many different choice variables. I mean, suppose t is some capital number t, say t equals 3. This problem is actually easily solvable. Okay, we just assume that this function is well behaved, then we can use some kind of equation of MRS equals the MRT, that kind of equation. We can easily get this problem solved. But when it is infinite number of period, this problem becomes really difficult. Okay, so I mean, I know that some people complain that I speak too fast, or I talk about this equation too fast during the midterm review. So any questions so far on this process? If you have too many questions that you feels like you don't want to ask the question, just randomly pick one and ask the question. No? Fine. Okay, so basically that problem is too hard. We're not going to directly deal with that problem. Okay, so notice that in this equation, CT plus KT plus 1 equals H of KT plus 1 minus dKT. KT actually determines the resource available for period T. Okay, so the resource that's available in KT sort of define all the future period, right? Because the KT will become KT plus 1 in next period. I mean, based on my decision of CT, but after I decide on CT, CT and KT together will decide KT plus 1. KT plus 1 will decide, and along with CT plus 1 will decide the KT plus 2, and CT plus 2 will follow then on, right? So sort of everything is origin from KT. So KT sort of decide everything or set the tone for all the future period. Or in other words, we learn something called the value function in the one-sided search model. What is value function? Now I have a more formal definition or formal way of writing this, like this. So value of KT is simply the maximized utility of this. This is basically, I mean, all the future period discounted back. The maximization, the maximized discounted sum of utility that I want to maximize. Okay, and I'm simply define the value of receiving or having KT started at period T as the maximized amount of this equation. So this is like, if I have that much KT at period T, what is my total value, sum of value in the all future, okay, all discounted future? Okay, and how do I calculate this? I mean, I don't know, but this equation can be rewritten as this. I simply move one CT, I move the S equals 0 part and the S equals 1 to the infinity part apart. Okay, because if this is not clear enough, this is wait a second. This is S equals 0, beta S U of CT plus S. S equals 1, beta S U of CT plus 1, and so on, right? And I separate them into two parts. The infinite part is just simply, again, the beta times S equals 1 to the power of infinite. And this is S minus 1 because I take one beta out. Okay, and this is U of CT plus 1, plus S. The same thing here. And this, because S equals 0, so this is 0, this is 0, this cross out. So that's basically U of CT. That's this term. Okay? But notice that this and this, aren't they very similar? Something looks weird. Oh, no, nothing. Okay. Aren't they very similar? In a way, these two are equal, except that this is for KT plus 1, this is for KT. Because this is start at 0, this start at 1. So the one that started at 1 is next period. Get what I'm saying? They're not exactly the same. They're different by one period, basically. If this is not clear, I can write out, you can try to write out this. This first term is U of CT. The second term is beta U of CT plus 1. The third term is beta square U of CT plus 2. And this, the first term is U of CT plus 1. The second term is beta U of CT plus 2. Right? So compare these two. The only difference is that I replace the T with t plus 1, then these two will be exactly the same thing. Okay? So what that means is these things after the maximization, I mean, that's basically these things, is v of kt plus 1. So that's just another value function. So I make the function recursive. V of kt equals a max of ct kt plus 1 and u of ct plus beta times v of kt plus 1. And this is called the Bellman equation. That's the key for this whole model. If you can derive this, I mean, you basically understand this model. If you cannot, you basically didn't understand this model at all. That's the whole key is in this equation. If you know how to derive it, you are a success. Okay, so to summarize, the social planner's problem become V of kt equals max of ct and kt plus 1 and u of ct and plus beta times v of kt plus 1. Subject again to this equation, the relationship between kt and kt plus 1. Okay, and given the assumption we have made about the function u and the function f, or basically the function h, there is a unique function v that solves the Bellman equation. Remember, this is because we have this strong assumption about the function. That's why we can actually mathematically prove there's a unique function v that solves the Bellman equation. It could be the case that you cannot find a solution to this Bellman equation, or there is more than one solution that are both possible. Okay, and we can even further simplify this equation because we know there's a relationship between ct and kt plus 1. That's basically this is the relationship, right? So I can use this and implement this into the ct here. And by doing that, the function become this. Oh, sorry. So v of kt equals, now you need to choose one variable, that's kt plus 1. Okay, and then the Bellman equation, the right hand side become u of h of kt plus 1 minus d times kt minus kt plus 1 plus beta times v of kt plus 1. Like I said, simply insert this into this ct. Okay, so I mean move this to here, so that's why there's a minus kt plus 1, and then the u of part, it doesn't disappear, right? So this is this part. Okay, and since the function v is concave and differentiable, this actually need to be proved, but let's assume that we have this, we know this, okay? But actually it's not that hard to prove, but I'm not going to spend time doing that, okay? And we can differentiate on the right hand side of this above equation to get a first FOC for this optimum. Okay, so basically we are doing, this is what I'm writing here. What I mean is you are doing a maximization of these things, right? So the easiest way is just what? You derive this with respect to kt plus 1 and make it equal 0. That's the FOC. So let's say this function is phi of kt plus 1. Then FOC is phi plum kt plus 1 equals 0. this is exactly doing that. Okay? Now, to determine this, we want v plot of kt plus 1. To determine that, what we can do is we can do something, we can use the envelope theorem. Right, this is why I asked the TA to review the envelope theorem for you guys in the beginning of the semester. Okay, envelope theorem, here what I'm using is basically that I can do a derivative here and sort of assuming that what I'm doing is simply doing the derivative of k with respect to kt for this thing. Okay? And since this is a partial derivative with respect to kt, this will disappear. And these will need a chain rule, right? So the first term is u plum of this. And then what's inside needs to be differentiated with respect to kt, and that's h plum of kt plus 1 minus d. That's this. Right? By envelope theorem, I know this I can write this equals v of v plum of kt. Okay, so we have this. This is this FOC. This is the FOC. This is by envelope theorem. And we can combine these two. How? I mean, we want v plum kt plus 1, but we only have v plum kt. How do I get v plum kt plus 1? I make t equals t plus 1. That's enough, right? Or I change t into t plus 1. So if this is t, I change it to t plus 1, t plus 1, t plus 1, t plus 1, and this becomes t plus 2. That's basically this. Okay, so this is v of kt plus 1, basically. V plum of kt plus 1. So this is, I basically replace this with this line. And this part just keep the same thing. Okay? And now, in the steady state means everything's constant, basically, in a way. We must have this. Every period kt is the same k star, right? So I can replace this with k star, k star, k star, k star, k star, k star, and k star. And then you do a little bit of math, you will find that basically this can cross out with this, right? Because this is h k star plus 1 minus d k star minus k star. This is the same thing. And they are both u plum, so this is the exactly same term. So this cross out. Okay, so this cross out. This become minus 1. This cross out. Okay, so it become minus 1 plus beta h plum of k star plus 1 minus d equals 0. Is this slow enough? I hope so. Okay. And if we have this, we can easily find that h plum of k star minus d equals 1 over beta minus 1. Okay, why do I write this? I mean, there are two reasons. Why? The first thing is I want this to stand out, the h function to stand out. The second thing is that what I write here makes sense. What is h plum of k star? That's the marginal product of capital in the steady states, right? The marginal product of capital, but the capital also are, depreciated, right? So there's a d term here. So this is, we call it the net marginal product of capital. Right? The depreciation is basically what's, wasted, right? So that's the marginal product will discount that. So it's a minus term. And this 1 over beta is what? Beta, we sometimes write beta equals this, right? Beta is the discount rate. And when I write this, beta equal 1 over 1 plus r, this r usually are the sort of interest rate, right? So beta over 1, that's 1 plus r, and minus 1, that's basically r. So this is the so-called subjective discount rate or interest rate. Okay? And what is the saving rate here? What is saving rate? That's basically the proportion of saving investment with respect to the of y, right? So it divided by yt, and this is, kt plus 1 minus 1 minus d kt. That's exactly the definition of it, right? And yt is simply h of kt. And in steady states, everything is k star. So this become k star. So k star minus 1 k star. The k star cancel out. So this 1 cancel out. So it's basically minus d k star. That's d k star. And below, the denominator is simply h of k star. So this is the saving rate in the steady states. Okay? That's it for this model. You see, this steps and the steps here or even here are not that complicated. Maybe the envelope theorem, you need to get a review. What that means. But if you understand, you don't need to know how to prove the envelope theorem. You just need to know that it is applicable here and use the envelope theorem. That shouldn't be too hard. And then you can get exactly what I have. The only difficult part is how to get the Bellman equation. So you need to be familiar with the way to write down the Bellman equation. Okay. I can almost guarantee you, I'm not 100% sure, but I'm 99% sure that there will be one question regarding Bellman equation or dynamic programming in your final. And by the way, I said this last year as well. And I think one student solved that dynamic programming problem in the final, or maybe no one. I mean, I don't remember exactly, but very few students were managed to do so. And I mean, it wasn't a really hard questions. I'm just I'm not even asking the student to derive everything by himself, by herself. I'm writing down step by step way of solving it. But students are still failing to do so. That's why I say this is the difficult part. Okay, so please spend some time, understand how you can write down the Bellman equation. Any questions for today? For this class, I should say, not for today. We still have another class. Okay. Okay, so if not, we will have a break for 20 minutes. So we'll come back. I mean, it's an online course. We don't need to exactly follow the school schedule. Okay, so we will come back at 3:20. Okay, 3:20 we'll come back and continue the next chapter.